With this worksheet, we get to practice naming compounds as well as calculating molar mass. Now, when we name an ionic compound, we start with the cation. So here we have potassium, and I know it's an ionic compound because potassium is a metal. And this part here, this is a nonmetal, and this is a polyatomic ion, and its name is nitrite. So this is called potassium nitrite. There's an I there. So to calculate the molar mass, I need the periodic table. Potassium is located here in row 4, column 1, and its atomic mass is given as 39.098 with this periodic table. We only have one potassium because it doesn't have a subscript, which implies that it is 1. And then we need to add a nitrogen to it. Nitrogen is over here in row 2, column 15, and it has a mass of 14.007. And then I also need to add the mass of 2 oxygen atoms. Now the oxygen atoms are given to me here at 15.999, and I need 2 of them. So when I add all that together, I get a molar mass of 85.103 grams per mole. Number 2 is called sodium bromide. And this one is easy to add up the molar mass. We need 1 sodium and 1 bromine. I'm already over here at bromine. So 79.904 is the molar mass of bromium. And for sodium, we have 22.99. So the molar mass is 102.894 grams per mole. Number 3, this is aluminum oxide. Now, even though we have our subscripts here because it's an ionic compound, we do not use the numeric prefixes. So this is aluminum oxide. We're going to need 3 oxygens and 2 aluminums. So I come over here, oxygen's 15.999. I need 3 of those. And aluminum is in row 3, column 13. It has a mass of 26.982, and I have 2 of those. So I have a molar mass of 101.961. And again, those units are grams per mole. Number 4, this is cobalt, and it is cobalt 2 chloride. I'm already over here at the halogens. Chlorine is in row 3, but column 17. Chlorine has a mass of 35.45, and I have 2 of those. And I need to add that to 1 cobalt. Now, cobalt is found in the transition metals. It's in column 9, and the mass of cobalt is 58.933. Add that to my 2 chlorines for a molar mass of 129.833 grams per mole. Number 5, we have a lithium, an oxygen, and a hydrogen. Now, oxygen and hydrogen, when they are bound together and form a polyatomic ion, it's called hydroxide. So this is lithium hydroxide. Now, oxygen is 15.999. Lithium is all the way over here on the left. It is in row 2 and column 1. So lithium has a mass of 6.94, and then we need a hydrogen as well. Hydrogen is 1.008. You commonly see hydrogen indicated as 1.01, but in this periodic table, we have a little more precision. So the molar mass is 23.947 grams per mole. Number 6, this is called calcium phosphate. This is an ionic compound, and because it's an ionic compound, we do not use numeric prefixes. So I'm going to start with calcium. Calcium has a mass of 40.078. I have 3 of those atoms. And then don't get tricked by all the subscripts. So although we have 2 phosphate anions, phosphate is PO43-, we have 2 phosphorus atoms. So I'm going to take the mass of phosphorus, 30.974, and multiply that by 2. And then I have a total of 8 oxygen atoms. And on this periodic table, I need to go backwards 15.999. So the molar mass of calcium phosphate is 310.174. And again, that is grams per mole. Now, there are a couple of tricky compounds down here, and the names are given to you. So trimethylarsenine. We're going to start with arsenic because it happens to be right here. In row 4, column 15, it is atomic number 33, arsenic. It has a mass of 74.922. I have one of those in trimethylarsenine. And I have 3 carbons. Carbon has a mass of 12.011. So I'm going to multiply that by 3. And add that to, let's see, I have 9 hydrogen atoms, 1.008 times 9. So I have a molar mass of 120.027 for that compound. Now, boric acid. Boron is an element we haven't used yet. Boron is over here. Row 2, column 13. So boron is 10.81. We have 1 atom in this molecule. I'm going to add that to 3 times 1.008, representing the hydrogen. And then I'm going to add that to 3 times 15.999, representing the oxygen. So I get a total molar mass of 61.831, and that is grams per mole. Now, glycine, we have 2 carbon atoms. Carbon is 12.011 for its atomic mass. So I multiply the carbon mass by 2 because I have 2 atoms, plus 5 times the mass of hydrogen, 1.008, plus we have nitrogen. Nitrogen is found in row 2, column 15, and its mass is 14.007 on this periodic table. I only have 1 of them. But I do have 2 oxygen atoms, so I multiply 15.999 by 2, add all that together, and I get a molar mass of 75.067. Again, that is grams per mole. Now, try Nitro Toluene. This is thrown in here because TNT is a fun molecule for general chemistry students to realize that it is still the molecule, and we can calculate its atomic mass. So when you have a molar mass or a molecular formula like this, don't be afraid of all of these subscripts. Just let the calculator do the work. So you have 7 carbon atoms, so 7 times 12.011, plus our 5 hydrogen atoms, so 5 times 1.008, plus 3 nitrogen, so 3 times 14.007, plus 6 hydrogen or oxygen, so oxygen is 15.999. Add all that together, and the molar mass of trinitrotoluene is 227.132, and that is grams per mole. Now let's determine the compound formula and then the molar mass from these compounds. So calcium chloride. Calcium makes a +2 ion. Chlorine makes a -1. So the chemical formula is CaCl2. So we need 2 Cl. Cl is 35.45. And we're going to add that to 1 calcium. Calcium is over here in row 4, column 2. And it is 40.078 for a total molar mass of 110.978 grams per mole. Potassium permanganate. Permanganate is one of those polyatomic ions you need to know. It is MnO4 and it is a -1. Potassium makes a +1, so they balance nicely. There is 1 potassium, so 39.098, plus we need manganese. Not magnesium, we need manganese. Manganese is found in column 7. It's a transition metal, and it has a mass of 54.938. And then we need to add in 4 oxygen atoms, so 4 times 15.999, for a total molar mass of 158.032, and that is grams per mole. Tin 4 hydroxide. So we're told that the tin is going to be in the 4 oxidation state, and hydroxide is a -1. So that means in order to make this compound, we must have 4 hydroxide units. So tin has a mass of 118.71, and we're going to add to that 4 oxygen atoms, so 4 times 15.999, plus 4 hydrogen atoms, so 4 times 1.008. And I get a molar mass of 186.738 grams per mole. Dinitrogen pentoxide. So this is a molecular compound. This is a covalently bonded compound, and I know that because it's given me the numeric prefixes. And the numeric prefixes make it fast and easy to make the chemical formula. So I need 2 nitrogens, so 2 times 14.007, and I'm going to add to that 5 oxygen atoms, so 5 times 15.999. Add all that together, I get a molar mass of 108.009 grams per mole. Iron 2 phosphate. Now phosphate is PO4 3-, and I'm told I have iron 2. So that means I must have, in order to make this compound make sense, 3 irons and 2 phosphates in order to balance those charges. So iron is a transition metal, and we'll find iron here in column 8. It has a mass of 55.845, and I have 3 of those. So I'm going to multiply that by 3 before I add in 2 phosphorus. Phosphorus is 30.974. It's over here in column 15. And let's see, I have 2 of those, so I need to multiply that by 2. Then I'm going to add in 8 oxygens, so 8 times 15.999. And that's going to give me a total molar mass of 357.475 grams per mole. Difluorine, so F2 decasulfide, 10 sulfurs. Sulfur is right under oxygen, and sulfur is in column 16. So sulfur is 32.06, and I have 10 of those. And I'm going to add to that 2 fluorine atoms. Fluorine is over here in column 17, and and fluorine is 18.998. So I have a total molar mass of this one of 358.596, and that's grams per mole. Ammonium nitrate. Now, ammonium is a polyatomic ion. It's a polyatomic cation. It's a +1. Nitrate is a polyatomic anion. It's a -1. So this is the compound formula for ammonium nitrate. Now, I have 4 hydrogens, so 4 times 0.008, and I have 2 nitrogens, 2 times 14.007. I have 3 oxygens, 3 times 15.999, and I get a total molar mass then of 80.043 grams per mole. Calcium carbonate. Calcium makes a +2, carbonate makes a -2. So this is the compound formula for calcium carbonate. So I'm over here with carbon and oxygen. I'm going to start there. I have 1 carbon and 3 oxygen. Now I'm going to add a calcium, which is found over here in column 2. Calcium has a mass of 40.078. I think I forgot a 9 on that oxygen. That's going to change the calculation only slightly. There we are, for a molar mass of 100.086, and that's grams per mole. Carbon tetrachloride. So again, we start with our carbon. Carbon is 12.011, and we need to add 4 chlorine atoms, so 4 times 35.45. I get a molar mass of 153.811 grams per mole. Copper 1 sulfate. Sulfate is SO4 2-. We're told we have copper 1. That means we must have 2 copper atoms to balance that sulfate anion. Copper is a transition metal. There he is in column 11. So copper is 63.546, and we have 2 of them. We're going to add to that sulfur, which is 32.06, and then 4 oxygen atoms, for a total of 223.148 grams per mole. To determine the mass of each of these samples of substances, I've gone through and I've calculated the molar masses already. I think we've done enough with the previous page showing how that's done. But in order to calculate the mass, we need to use that molar mass, and we need to use it as an equivalency expression. So we do that by using what we're given. So 0.576 moles of our compound. In this case, it is calcium carbonate. And I need to use the equivalency expression with moles in the denominator of my calcium carbonate and grams of calcium carbonate in the numerator. So it's important to understand how the molar mass units work. The molar mass units are grams per mole. So the number I'm given, the 100.086 that I've calculated, that is 100.086 grams of calcium carbonate per 1 mole. So the moles cancel out and I'm left with grams. So I take my 0.576 and I multiply it by the molar mass, 100.086, to get 57.649. Now I need to pay attention to my significant digits. I started with 3 significant digits. I can only report 3 significant digits. So 57.6 grams of calcium carbonate. For mercury, I have this mercury 2 oxide. I start with what I'm given. So I start with 2.3 moles of my compound, HgO, and I use the molar mass, which is 216.589, and that is grams of HgO per every 1 mole of HgO. So 2.3 times 216.589, and I get 498.15, but I only started with 2 significant digits. I can only end with 2 significant digits. So I would put this in scientific notation and call it 5.0 times 10 squared grams of HgO. Similarly, I'm going to take the moles and multiply by the molar mass in order to get my grams. I have 3 significant digits. I need to end with 3 significant digits, so this would be 488 grams of S2F10. Number 4, I'm going to take 0.17 moles and multiply it by 124.096 grams per mole. I started with 2 significant digits. I end with 2 significant digits. 21 grams of, let's see, this is an ammonium 4,2. I don't have my glasses on. I think that's what it says. Number 5, we have 11.8, and I'm going to multiply that by 83.976 to get 990 grams. Now I started with 3 significant digits. I end with 3 significant digits. Look, I have a 9 out here, so I can round that to 991 grams of my compound. Number 6, 0.088 multiplied by the molar mass, 134.863, and I get 11 point something or other. I have 2 significant digits in my measured quantity. I can only end with 2 significant digits, so this would be 12 grams of my compound. Number 7, I start with 0.43 moles. I multiply it by my molar mass, 37.954, and I get 16.32. I started with 2 sig figs. I can only end with 2 sig figs. Lithium, aluminum hydride. Number 8, I start with 6.42 moles, and I multiply it by 201.09 grams per mole. I started with 3 significant digits. I need to end with 3 significant digits. So 1290. That 0 is ambiguous, but it is not significant here. You could leave it like this. That's okay. I am not likely to count you off for that. So 23.25 moles times the molar mass, 136.134, and I get 3,165. I started with 4 sig figs, I end with 4 sig figs. So 3,165 grams of my compound. Number 10, 3.37 moles multiplied by my molar mass, 294.181. And I get 991 grams. Started with 3 sig figs, end with 3 sig figs. And I need to declare the compound. And activity 2, we're going to take, in this case, our grams. We're going to start with grams of compound. And we're still going to use that molar mass as a conversion factor. Now, the number stays with grams, so this time the number goes in the denominator, and moles, or 1 mole, goes in the numerator. So to do this, I'm going to do this math. I take what I started with, 75.2, and I'm going to divide it by the molar mass. And then I end up with moles. Now, you do need to pay attention to your significant figures. You started with 3 significant figures. You end with 3 significant figures. So this would be 596. Look to the right, it's a 9. So I'm going to round that up to 0.597 moles of compound. Similarly, I take the grams that I start with, 22.3, and divide by the molar mass, 73.888, in order to get moles. 3 significant figures to report, 0.302 moles of my compound. Number 13, 182.1 grams divided by the molar mass, 136.056. So I end, let's see, I started with 4 significant digits, so I'm going to report 1.338 moles of my compound. Number 14, I have 12.6 grams. I'm going to divide that by 44.097 grams per mole. Started with 3 significant digits. I report 3 significant digits, so 286.286 moles of my compound. Number 15, 76.54 grams. Divide that by my molar mass, 76.341. And I get almost 1 mole. So I started with 4 significant digits, so 1.003 moles of my compound. Number 16, 235 divided by 144.047, and I get 1.63 moles of my compound. I started with 3 significant digits, so I have to end with 3 significant digits as well. Number 17, 2.14 grams. I'm going to divide that by 60.686. That's my molar mass. And I will report 3 significant digits, 0, 3, 5, and I would round that up, 3 moles of my compound. And number 18, that's too many digits, 4.12. Divided by 234.05, and I get let's see, I started with 3 sig figs, end with 3 sig figs, 0.176 moles of my compound. And finally, number 19, 96.8 divided by 182.893, and I get 0.529 moles of my compound.